So this morning we'll focus on simulation, or some parts of the nuts and bolts of simulations. And so the first thing, Ralph Archuleta, who's the working group chair for simulations, recently took over. He's going to go quickly over kind of what their scope is. After that, we'll have Ruth Harris talk about the inputs to dynamic rupture models. And Ralph will talk some more about kinematic models. We'll have a discussion, and then Rob Graves will come back and focus on different kinematic rupture generators, see what is out there and what can be used. There was a slight change to the schedule for this afternoon, and we have the updated Thursday agenda is available now on the table outside. Thank you so much, Carola. So Ralph?
So the Finite Fault Simulation Working Group is first of all charged with the idea of looking at, as Ye-Hua explained 2 days ago, 6 different methods for calculating ground motion from different approximations. They're all kinematic models, but approximating a finite fault and calculating the ground motion. The ultimate objective is to calculate ground motion at a distance range 0 to 1,000 kilometers and 0 to 100 hertz, which is a very daunting task, I can tell you numerically. And we're still getting into that. The Finite Fault Simulation Working Group is yet to actually define, and I will explain this later this afternoon, we have issues basically with how we're going to validate the methods or compare them for the 7 selected earthquakes. And those 7 selected earthquakes I'll go over this afternoon as well, but we have 7 selected earthquakes in which we are going to be computing ground motion. We've yet to determine the number of stations or, in fact, the source model, the low-frequency source model that would work. So in starting this off, the next speaker, Ruth Harris, will be talking about work that's been going on within SSHAC and elsewhere, in fact, but how to calculate ground motion from finite faults and some of the issues that you really deal with, given the fact that we're going to be using kinematic models, but in fact, most of us know that if we could really get the full physics of an earthquake rupture, we could do the dynamics. And at least we think we could numerically simulate earthquakes dynamically and really represent the physics and really get true ground motion within the certain approximations, of course. But so with our group, what we're charged with then is calculating the ground motion from finite faults. And we have a variety of different methods, as Ye-Hua explained. And each of those methods has certain strengths and certain weaknesses. They're not as yet as complicated as the methods that Ruth is about to show, but at the same time, they embody some of those basic features. And so I'll be talking more about that this afternoon, and I'll be talking a little bit about after Ruth, but I don't want to take any more time from Ruth. We're at the embryonic stages, basically, of these finite fault simulations in the sense that we are actually trying to determine which models we want to go forward with for doing these calculations for the Central and Eastern North America project here that we have. So we're really getting started on this to see which of these models will work. And Ruth is going to talk about a method, a fully dynamic modeling method that has been used within SSHAC in order to estimate ground motion for another critical facility, but she'll explain all this to you. So Ruth is up next.
Okay, I'm going to talk about the 100 Runs project and then also code validation, a big exercise that we've been doing, USGS and SSHAC researchers have been doing together. And I want to thank Norm and Christine for inviting me to give this presentation. And I'm learning how to use a PC very quickly. Okay, so in our lives, we've often experienced the results of the motion that you see on the left. And the mouse is not quite working. Ah, there it is. Okay, we've experienced regular ground motion. Then also a few people that are here have probably experienced, not quite up close, but maybe in the distance, some extreme ground motion. And these are both examples from the nuclear test site, Yucca Mountain region on the left, where for tens of thousands of years at least, there have been no big events, no strong ground motion as observed in the geologic record. And on the right is extreme ground motion, but this is actually from a nuclear blast, a test blast. So this is not something that would be generated by a tectonic earthquake, but performed a lot of damage to the rocks. So one of the things that we're trying to see is what's the probability that you'll get regular ground motion, say in a site near the formerly proposed nuclear waste repository at Yucca Mountain, and what's the likelihood, is there any likelihood at all from dynamic rupture models that you might also see extreme ground motion. So geologically we think we've never seen this, but is there any probability at all that this could happen? And this is the point of the 100 runs exercise, and I can't come all the way to conclusion because it's still in process, but I just want to show you what we're doing and the progress that we've made so far. Okay, so we're doing a computational project. I think on Monday I was listening in and it was really great presentations and I could hear the sound perfectly. We saw a lot about data, heard a lot about data. This is a purely computational exercise, so we should have an easy time because data is much harder, but you'll see we even have some challenges also. So because it's a computational project, we have to make sure that our computer codes work okay. And once again, you think that would be simple, but these codes that we're using have no analytical solution, so we have to do lots of tests and inter-code comparisons to make sure that they're functioning properly. So our goal for this is to determine if our codes can produce repeatable, both regular and extreme ground motion. For the 100 runs exercise, we were tasked by Norm to see if we could produce a range of magnitude 6.5 earthquakes. So this is probably an unusual exercise that we actually had to produce a specific magnitude, and maybe this is a challenge that we have right now. A magnitude 6.5 earthquake on the Solitario Canyon Fault, which is near our formerly proposed nuclear waste repository. So we had a workshop to try to figure out how you do that. What are all the different parameters that you should vary to get magnitude 6.5? Then in number 3, we chose a method, and we also have had peer review to see if what we're doing makes sense. Then this is where we are now. We're conducting 2 threes. We're very efficient. Conducting the 100 runs exercise and then summarizing the results. Okay, so our first big thing is we have to make sure that our computer codes work okay and determine if we can produce repeatable ground motion and also slip patterns on faults. So this is a big exercise, very congenial, collaborative group, and this is just showing the people that are currently involved. Mostly, I should say everyone is involved in the Southern California Earthquake Center, and then we have people both from the U.S. and some international participants. They range from students up to senior faculty and researchers, and we're continually, people graduate, they go on to do other things, maybe go work for oil companies, and then we get new people coming in too. And then we have a core group that's been participating for the whole time. Okay, and if you want more information, I encourage you to go to our website, scacbeta.usc.edu/cvws. And there's also a paper that was published in January of 2009 in Seismological Research Letters. Okay, so the overall goal of our code verification group is to compare the methods that are being used by SCEC and USGS scientists to simulate spontaneous dynamic earthquake ruptures. So the previous talks that you've heard have been for kinematic models, and they have some similarities but also some differences, and they require a lot more input parameters. So some of our specific objectives are to understand if we get the same results, if we use the same assumptions. We have a lot of assumptions, and there are no analytical solutions. The only analytical solution that's out there is for one where a rupture propagates at a constant speed and just goes forever, the Kostov solution. So everything else that we do, you either just have to believe that the person got the right results, or nowadays, because so many people are doing these models, you can actually compare the results doing different codes, and that is what we do. And we've had funding from SCEC, USGS, the DOE, PG&E, Extreme Ground Motion Project, and also PG&E. And I think in the past we got some money from NGA. Okay, so here's how these things work. We have in red these computer programs, except I'm told they're now called codes, computer codes that simulate earthquakes and spontaneous ruptures, and they have a lot of assumptions. Some of them are assumptions that you also need for kinematic models. For example, for a kinematic model, you'd also need to know what the fault geometry is. And the material properties, you'd also need to know the shear wave, velocity, the shear modulus, density, all those things. We also sometimes assume things are elastic behavior and sometimes plastic behavior, which you might or might not do in kinematic. So these are have some overlap with the kinematic models. But where we diverge from the kinematic models are prescribed the slip, but we don't. We start out with assumptions of what the initial fault stresses are, and then we go from there. And this is the trick. How do you assign the initial fault stresses? And this is one of the things we had to figure out for the 100 runs exercise, 100 source realizations. We're going to do this 100 times and try to figure out what's the best way to present these initial fault stresses. We think that the stress on faults is not homogeneous. We get very different earthquakes, probably complete stress drop giant earthquakes and really super shear ruptures all the time. So we are pretty sure it's not homogeneous, but how do you quantify the heterogeneity? And that's where we are now. We don't know, but we're trying. Then in addition, for these simulations, you also need a failure criterion, something else you also do not have in the kinematic models. And these failure criteria determine if and when the fault can slip. So kinematic, you already assume that you know how far it's going to go, and you're just trying to figure out stuff from there. But here, we don't even know. Once you start an earthquake, we don't even know, are you going to get a 3, or are you going to get a magnitude 4, 5, 6? So this is another one of our big assumptions, and also a major topic of research. How does earthquake friction, fault friction work? So for this exercise, we've assumed slip weakening, but there are also many other possibilities out there. Most likely slip weakening is too simple. But it's just something we've tested so far. So we're using it in our code validation exercise. We've also done some rate state friction, and this year we're going to actually also look at thermal pressurization. So there are other possibilities. Okay, so you plunk all this stuff, all these assumptions, into your code that simulates earthquakes as spontaneous dynamic ruptures. And out of this, if you're lucky and it works okay, you get ground shaking seismograms throughout the medium. At wherever you want your stations, you can get those. You can look at fault slip. If you wanted to, you could also look at how much heat generation there is, many different parameters. For us, we're going to be looking at the ground shaking, ground motion, and then also at the fault slip. Okay, with the mouse. Oh, perfect. Okay, so this is what we've done. In many of these exercises, code comparison exercises for all different groups, and we have a lot of them. For example, in SSHAC, people are looking at geodesy, transient motion detection. Now we now have people that simulate tens of thousands of earthquakes in really simple models, all sorts of things. The recommendation is always start simply and then get more complicated. So we too had to started more complicated. We started with a half space, and then we backed up and went to a full space. So this is how these things work in general. This is the first regular one that we did. This is for, get the mouse under control. Starting, my mouse is not visible. Nope. Got it back. Okay. So we start in the middle of a fault, and you assume that you have artificial nucleation. In full cycle models where people are doing whole earth sequences of earthquakes, you might already be able to spontaneously nucleate. We don't. We assume you nucleate in some area. And then the mouse just went away again. Okay, so you start in the middle, and then you propagate out, and then it's you might get to the edges of the fault, or you might not. And then it's for the models we've been doing, you stop at strong barriers. All right, so on the bottom, there it is, the mouse again. On the bottom right, one of the things we've been looking at is rupture front contour plots, and these are very diagnostic about whether or not your ground motion will match. So this is just once again looking at the fault surface, and I have my in and out mouse that sometimes appears and sometimes doesn't. So if you just look at the lower right, it's just the fault surface, and it's showing you where the rupture front is in 0.5 second intervals. So you can see it starting in the middle and then propagating outwards till it reaches the top of the fault and the sides of the fault. So what we found is when we have a bunch of modelers do this, and for this case I'm showing 2 different people ran this simulation. If these guys overlay each other perfectly, then most likely our ground motions also match. And in the lower left, and maybe see it up there? No. Okay, in the lower left, there's some seismograms, and those are for the top of the fault. Okay, mouse came back again, yes. All right, so we've been doing a bunch of these benchmarks. That was the first one, a simple full space one. We then did a half space. We did some very light and heterogeneous initial stresses. Then we did the bimaterial problem, heterogeneous stresses. And these are all slip weakening friction and vertical faults. Next we did, nope, didn't go. Click. Got it, okay. Then we did depth-dependent initial stresses, and then we were trying to get towards the solitary canyon fault scenario, so we know that's a dipping fault, so we gradually got there with a vertical dip slip fault. That's seen in nature, but important to make sure we make progress incrementally. Then we finally did go in the right to the dipping fault with regular ground motion. So this has all been regular ground motion, subshear ruptures, behaving pretty regularly. And then we finally got to the extreme ground motion case. So this had strong, very strong super shear, dipping fault, and just pure dip slip. And we did that the elastic case on the left. Elastic case on the left, and then with plastic yielding on the right. So for each of these, we're varying something one step at a time and just seeing if all our codes can match. Okay, so the last case I was talking about with extreme ground motion is directly relevant to the solitary canyon fault. And what we were trying to do is to see if we could replicate the results in the Andrews, Hanks, and Day of the SSA 2007 paper, where they are estimating what the maximum possible ground motion could be at the repository. So we did this case, but we did lots of different stations that are on, you can see on the figure on the right, all the stars at the top are all these different stations we looked at, and one of these is the repository on the close side of the fault in the footwall. And we looked at other stations too, and just to see if we could get a good match. Okay, so we did the case, we did a bunch of cases. So I go back to this. We did a bunch of cases. We did elastic in 2D and 3D, and we also did plastic off-fault yielding in 2D and 3D. And the reason we did this is because the Andrews et al. Paper was just 2D modeling. So we really want to know, many times people do computations in 2D and they'll say, oh, that's the same as 3D. Well, Joe's a smart guy, so of course he did not say that. But some of the other simulations that people do might be in 2D. And then we also wanted to compare the elastic and plastic. So in the Andrews et al. Paper, they did do the simulations in 2D, but they also said that was definitely going to give higher ground motions than 3D. So we wanted to check that and see. Okay, so we had a bunch of people. Each of these names in here, you have all these different names, and each of them is using a different code. And so this group of people did the 3D elastic case. This group of people did the 2D elastic case, and there's some overlap among the people. This group did the 3D plastic, and this group did the 3D and 2D plastic. Okay, and here are our results. Looks okay. This is the vertical velocity just at the repository station. And these are all the different people that are running it. All the results are all the same, and it's going on the vertical axis from 0 down to -6 meters per second, and the horizontal axis is 0 out to 8 seconds. And this is has a 3 hertz Butterworth 2-pulse 2-pass filter. The filtering made a little difference, but not a huge amount. So anyway, so you can see there's a really good match, that the codes are all producing the same things. And what this is showing is that Joe's code, which is one of the codes that did the 2D simulations on the bottom, his code, you can't tell the difference between his results and everyone else's results. So in other words, his results for the Andrews et al. Paper that predicted maximum possible ground motion on the Solitario Canyon fault, we've been able to reproduce it. The assumptions that we used are a little bit different, so I should say we were able to reproduce what his code does. We also can see, so this is the vertical, and then we also have the horizontal, and this is the fault trace perpendicular horizontal. Once again, decent matches. And we can also see that the 2D, that the elastic, which is on the bottom, does give higher ground motion than the 2D does give higher ground motion than the 3D, and that was one of the suppositions in the Andrews et al. Paper. Okay, so we made sure that our codes worked. They seem to be working okay for the simulations that we've done so far. And now we're off to the 100 runs project. And we have to figure out how to do 100 magnitude 6.5 sources on this Solitario Canyon fault, 60-degree dipping normal fault. Okay, so now we still have our same codes participating, the thing in the middle that the mouse doesn't want to point to. And we have the geologic structure fixed. So we have this fixed. But now we have 100, we're trying to produce 100 sources. So we're going to be assigning our friction parameters 100 times. And we're also going to be assigning our initial stresses 100 times. So we're going to be varying these, mostly concentrating on the initial stresses. And out of this, we're going to get 100 different models of fault slip, or also 100 different models of seismograms. So we tested our codes. We think they're working okay. And then we have to figure out how to do this part. Okay, so we had a workshop back in May, and we invited 5 groups of people to talk about the methods that they are currently using to generate heterogeneous stresses, and a lot of them are overlapping with people that are doing the same thing for the kinematic models. So we had a bunch of different groups present, and then the goal at the end of the workshop was that we could come up with a method that we would then adopt for the spontaneous rupture exercise. Okay, so we had 5 really great presentations, and at the end of the day, it turned out that we had 5 great presentations, but none of them had explicitly described their method so well that we could just take it off the shelf and go implement it. So instead, what happened is we started looking individually at each of the methods and then also consulting with the authors of the methods, and we decided that we would take a hybrid method or construct a hybrid method. So we chose a method, actually constructed a method, and then we requested a review. So these are the features of the method we're using now, and we know that we need to improve it. Our method is not good enough yet. We have our gradual force nucleation that we've done before, slip weakening. We have to use that because we've tested in the code validation, rigid barriers. This is the size of our fault plane. We have a depth-dependent stress distribution for the normal stress. And then our initial shear stress distribution has 1-point statistics that are Levy distribution and 2 points that are von Karman power spectrum. Magnitude 6.5 is our assignment. We have a simple 1D 3-layer shear modulus or velocity model. And then for now, we're doing elastic behavior. For extreme ground motion, plastic behavior made a pretty big difference. But for now, we're starting with elastic because this is mostly going to be regular ground motion. Oops. Okay, so we chose a method or constructed a method, got review, and now this is where we are right now conducting the 100 run spontaneous rupture, dynamic rupture exercise. So they have 3 people were chosen because their codes match pretty well in their code validation so far. And this is Michael Burrell, Ben Dwan, and Shom Ma. And they have finished the runs, and their assignment was to do 100 runs, and they've actually done 200 runs, which is good because in the proposal I said we'd do 30 runs. So we've exceeded expectation in that respect. And right now, the results are being summarized and archived, and we're eagerly looking forward to our funding for the archiving, which I know will be arriving soon. And then as soon as we're done with this, our fault slip distributions that we will have gotten for our 100 to 200 runs will be provided to the people who will be doing the kinematic rupture simulations. We can take this all the way to ground motion, but for the spontaneous rupture, we generally are looking at lower frequencies. So kinematic rupture is needed, and we also can't go really far distances. So we need to have it transferred to kinematic rupture modelers to take it further. Okay, so we've done all these things. We've done the runs for the spontaneous rupture, once again, 2 3s. And we need to summarize the results and provide recommendations for future activities. And in case you're curious about what our heterogeneous initial stresses look like that we need to fix, this is just one of our cases that we've done using the assumptions of a few slides ago. In the colors are just showing you the blue means you have a lower initial shear stress divided by normal stress, and the red means you have a higher value. It's not smooth, and that's probably something that we need to do, and there are probably some other things we need to tweak. So given this initial stress distribution, just quickly show you the results. This is one of those rupture front contour plots. This is just looking at the fault itself and the progress of the rupture that, for this example, started here, artificially nucleated, then propagates out. One of the problems we're having is that you see green, red, and black, and they should be overlaying each other perfectly. They are not. And then also in the upper left corner, the codes This is where you're hitting the Earth's surface, so in order to get your ground motion matching, these better also be matching. These are not matching, so we have a little bit of a problem here that we have to deal with. So in the perfect world, we would have had all these matching perfectly, and then especially at the Earth's surface, which is your ground motion at the Earth's surface. Okay, and then here's a comparison of the seismograms. This is once again at that formerly proposed nuclear waste repository station. This is a kilometer off the fault, and it's at 300 meters depth. So showing the three components, fault perpendicular, fault trace perpendicular, horizontal velocity in the top. And this is going from the vertical axis is +1 to -0.2 meters per second, and the horizontal axis is 0 to 15 seconds in time. These are not filtered. So the three components, the largest of course being the fault trace perpendicular, but and the match would be really great if this were like modeling versus data, but it's not, it's modeling versus modeling, so we really need to get that a little bit better. This doesn't look too bad. If you looked at the surface station though, it would not be this good. So we clearly have work to do. Okay, so this is the to-do list for us. We need to archive and summarize our results. And then we have to figure out if our heterogeneous conditions assumptions are consistent with the hypotheses behind them and develop a new hybrid method. We know that the heterogeneous initial conditions method that we're using right now is not the optimal method. We don't know what is an optimal method, but we need to work some more on that. And then we have to figure out the reasons that our codes aren't matching perfectly. It's most likely because the heterogeneous stresses are way more complicated than anything we've done before. We also have to deal with cohesion. There are lots of other parameters that we've not had before. And the way we're going to narrow this down is for 2011 in our code group, we have a heterogeneous stresses benchmark that we're going to do for a vertical strike slip fault. And that's it.
Before we start on something on questions on Ruth's presentation, I want to go back and actually give you a little bit more introductory so that you will appreciate what Ruth has just done. So can you help me get this one in here? So just quickly, to put things back into our focus as to why are we doing all of this stuff that Ruth just talked about. It's a huge effort. We are having to generate in our finite fault simulations ground motions up to high frequencies. And really the only practical way for us to do that is kinematic models. We've done this before many, many times. You know, had groups do lots of realizations for us, and we have not gotten we've gotten a lot of deviation in results, and whether that's true epistemic uncertainty or not has been an issue. The key issue that we get here is how we're going to define our inputs to all of these kinematic runs, the source inputs, particularly, you know, getting averages and variabilities. And we want to avoid creating unphysical combinations of parameters. Right, so if we take marginal distributions of a slip distribution or of rise time and rupture velocity and so forth, we can make combinations that are never going to happen. You can shove them into your kinematic model and get numbers out, but we can get huge value. Some of this were issues when we ran the Pegasus project and asked kinematic modelers, how big can you make ground motions? And the answer was very big. Okay, so they could find combinations of kinematic parameters that produced huge ground motions. And whether those were actually things that could happen became a question. So the idea here was how do we get at controlling dynamic properties for input to the kinematic model? And we can use observations, and I think what you'll hear later in terms of what Rob Graves is going to talk about are some sort of statistical parameterizations of past earthquakes when we've looked at slip inversions. But the idea, what we're trying to get at here is how can we try to get back more fundamentally to what are these correlated parameters? And so what our goal is to use a dynamic rupture model to generate suites of sources that will have correlated source parameters through the constraints of the way the dynamic models work, and then those can then be put into the kinematic models, okay? So we've moved the problem in this approach of defining the inputs from the kinematic people to the inputs to the dynamic people. And what Ruth is talking about is as they're trying to do this now really for to be able to specify all the possibilities, they're finding some difficulties that they're starting to work with. And the 100 Runs project was a first attempt to really push this whole thing through to practice and trying it out. So what we're looking at is validating the models. That's really important for us. What Ruth talked about as you listen to things here, we don't allow them to go to change their models and say, all right, we've validated all these slip weakening models, now we'll go use some other approach. Okay, so we force them to use the models that have been validated. Specifying a way to get the inputs is what Ruth was just talking about. Running these cases, so now we get 100 realizations of a future earthquake of a given size. That creates for us, in one way, a library of possible sources. And then there's two approaches. We either take those libraries and directly input those into the kinematic models, or you actually can describe those by some statistical properties of how the slip and the rupture velocity and so forth, what their variability is and how they're spatially correlated. My view is that our biggest problem in kinematic models has been we have not tracked the joint distribution of the input parameters. And I'm not sure that will turn out to be the case, but I think that has been a fundamental stumbling block. So our goal of using the dynamic rupture models is to get at joint distributions of all of these dynamic rupture problems in space, across the fault, and at a point between different parameters. And so that 100 Runs project, we're doing a trial application, trying to figure out what works, what doesn't. There is going to be a follow-on this in the next year, moving to a strike slip earthquake and trying the same type of problem to see if we can improve what Ruth has been talking about. For us here, this is happening at a pace that is probably going to maybe be informative to what we need to do, but I'm not sure it will make the schedule that we need for the NGAEs. But we still need to be able to think about what's coming out of this. And I think what you're going to see following on now, Ralph will talk about some work that they've done to already follow this approach of parameterizing these library of sources in terms of their statistical distributions and their joint distributions. And then Rob will follow later with more of what is the current practice and all the ways that people generate inputs for kinematic models. So that's what we're talking about here, okay? Ralph, and then we'll have the discussion afterwards. So you can just close that one. Can you give me the... I forgot to have you start with that bit of a summary.
So I noticed that this is the first day actually we're behind schedule, but that's okay. I'm going to be a little bit ahead. I'll go rather quickly. This is a paper that has been published in JGR. I'll come back to it later and give you the reference. But we have been looking on strike slip faults, basically trying to use these dynamic models in order to infer the correlations that we can then put into the kinematic models. And, you know, in the kinematic models, the big thing about them is that if you've got them, you can use them in general to run to high frequencies so that you can get to the frequencies of engineering interest You can compute the Green's function so that for a particular area, which means that you can run hundreds of different models, and because you're summing a bunch of subfaults, computationally it's really embarrassingly parallel problem to use on a computer. The main assumption when you do kinematic modeling is that we actually know how an earthquake will rupture. So basically, when you do kinematic modeling, you get to act as God. You say, okay, I know what's going to happen, and we'll just calculate the ground motion that follows. But in fact, if we really want to get a better understanding of these kinematic models, then what we've got to do is we've got to look and see what we find from the dynamics, from the physical models that represent an earthquake rupture. And so Ruth has already shown this, that you put the different elements in to the best of our knowledge. There are different problems, and each part of here basically about initial stresses all the way to the failure criteria, but at least we can explore these possibilities as well. And in many ways, they're what we would call epistemic uncertainty with regard to the dynamic models. But let's suppose we can run these dynamic models. Then the idea here is that we would like to construct kinematic models that really capture the main characteristics of the dynamic rupture models. This is really the goal that we're set out, okay? Now you start off with this, with the idea, we started off with a paper by Lou, Archuleta, and Hartzell in 2006, in which we started to look at what would happen if we used correlated source parameters, correlated kinematic source parameters, namely the slip, the average rupture velocity, and the rise time. And in fact, when we were doing this, we guessed, okay? We've checked with Northridge, just one example, and with one example you get an answer, of course. But the idea was that, the basic idea was that on any one of these, in the slip or something like this, you talk about slip on the fault, you really don't know before an earthquake what that slip is going to look like. And so we said, okay, well, if you look at the slip, there are reasons for doing this, but we looked at a truncated Cauchy distribution and said, okay, there's some maximum probable slip, but there could be, there could be tails on this slip that are much more than the average slip. It can't go to zero, so it's going to be truncated at zero, of course. And then you have rupture velocity. It's the same thing. In other words, you don't know what the rupture velocity is before the earthquake, but we have good estimates looking at analyzing data that the rupture basically lies between 0.6 and 1 if you look at the ratio of the rupture velocity to shear wave velocity. We're ignoring super shear at this case. And you can make an approximation. We used a beta distribution for the rise time at the fault, saying, okay, there's a certain probability it'll be around here. It won't be longer than the total rupture time of the fault. It probably won't be shorter than some number either. And we put these distributions in, so we're selecting them, but then we correlated these. We found we used a method to correlate this. I'm not going to go into it at this time. It'd take too long. So the idea was that we wanted to you have to click here, isn't it? Okay. So what we're looking then is that what we wanted to do is actually look and say, well, what are these parameters? What are their marginal distributions, basically? And a very important thing is what is the autocorrelation of these parameters on the fault? And in particular, we have some idea of what the slip might be, and from there we can derive actually the autocorrelation for the other parameters as well. And, there's a lot of uncertainties. I mean, this group knows this really well. And, but the idea is how do we capture these uncertainties? And we tried doing this by looking at, the aleatoric uncertainty by computing a lot of realizations of dynamic ruptures. And for epistemic, we tried basically to use other approaches and data that came from other places. And so, we collected a lot of ruptures. In fact, we calculated over 300 ruptures, dynamic ruptures. And then we make maps of these parameters. And then for all of these ruptures, we're going to compute the correlations among the parameters, the autocorrelation and the marginal distributions. And so we had small ruptures. These are all strike slip. And one of them that we used, in fact, we used 6 models from the DynaShake method of SSHAC in Southern California. The rupture is 300 kilometers long. A lot of our models were basically in the range of, when you look at them, they're in the range of about 6.5 to 7. And, we're looking at velocity models that sometimes they're in a half space, sometimes it's a layer over half space, 1D gradient. But one thing we did, because we were calculating these, we calculated them all up to 5 hertz. So we have some pretty high frequencies on this. They're much higher than normal. And I'm not going to go into entirely what goes on, but basically we find a way to determine basically how we're going to get the autocorrelation of the slip on the fault. Okay, so and we do the correlation from the slip, we get to the stress. Remember that in these dynamic models, the parameter that's going into the dynamic models is the initial stress, the friction law, and then some measures of the strength of the fault and sliding friction. And we have ways of estimating what that number should be or what that correlation should look like. And we can vary this. In fact, I will show you that if you vary the autocorrelation of stress on the fault, you can get sometimes very large amplitudes and very fast ruptures. Sometimes you get ruptures that just want to stop, but you can make them extremely heterogeneous depending on what the autocorrelation of the stress is on the fault, which will lead to what the autocorrelation of slip is on the fault. And so I'm not going to go through all this. It's in the paper, but there are lots of different parameters that you can play with. But basically, there aren't that many. You know, you have a stress drop, which we've been talking about. We keep ours to basically about 3 megapascals, about 30 bars. So, you know, where we have different D sub C and things like this. But basically, we've got all these parameters. And then we calculate, after we run these parameters, we calculate on the fault what is the final distribution of slip. And we calculate what we call the kinematic slip, what fits through here to a slip rate function. And so that we can talk about total slip would be the total integration under this slip rate function. But we talk about a parameter that basically matches a kinematic slip model, because in a kinematic slip model, we're going to specify that slip rate function. And when you specify that slip rate function, it will have an area underneath it, and that will be the kinematic slip that we're going to put into these kinematic models. And there's a total slip, if you'd like, but you look at the kinematic slip, we can then calculate what it looks like because we've got lots of points on the fault. And so the reason I want to put this picture out here is that these are parameters that are in fact related to the kinematic parameters, namely the start time, which is basically giving you your rupture velocity. There's going to be a peak time, the time at which the slip rate pulse reaches its maximum. There's going to be a total rise time, a typical parameter that we would have in calculating a kinematic problem. And of course, we'll have the total slip or the kinematic slip. In other words, and most of the time we'll be talking about kinematic slip that we will have. So these are parameters that you can compute that we have to see how they're correlated, because they are the ones these are the parameters that we are going to stick back in to those kinematic models. And so we calculate the correlations for all the different parameters. And we've got, we take an area on the fault that's away from the edges, not including the free surface, away from the hypocentral region, and we calculate the correlations within a box. And in this case, we limited ourselves to those parameters which are sub-shear. And so this is what it comes down to. In other words, we do correlations, let's say between kinematic slip. This was the parameter that Peng Shan and I and Steve got wrong, okay? And we had in the original paper that the rupture velocity and the kinematic slip were correlated. But when we did all these runs, what we find is that, yes, there's a nice distribution around here, but in fact, the median or the mean is centered around 0. In other words, there's no correlation between kinematic slip and rupture velocity. On the other hand, you can see that the kinematic slip and the rise time are correlated. There's a positive correlation out here. And the rise time and the peak time are slightly correlated. They're certainly off of 0. There's a negative correlation if you look at peak time and rupture velocity. In other words, you get shorter peak times for faster rupture velocities. Not too surprising, I would think. And you also see that between the peak slip rate and rupture velocity, there's a positive correlation, which you would expect. And these are the type of correlations that we've got to put into these kinematic models in order that we understand, what is allowed. In other words, we cannot choose to put and I'll point out, you'll see that if you use this, as we did, because, some models could have a positive correlation, and some models would have a negative. But on average, your kinematic slip and rupture velocity should, in fact, in the calculations we've done so far, indicate 0 correlation. So we made a correlation matrix, and It's the easiest one to see. This gamma here is the ratio of the rupture velocity to shear wave velocity. Okay, and in this case, we were only looking at sub-shear, so it's a number between 0 and 1. But yeah, obviously slip is correlated with self. It's slightly correlated with rise time. We've got a stronger one. But slip has no correlation with rupture velocity. And so over in here, we see negative correlations, let's say, between peak time and the rupture velocity. And we see correlation between peak time and slip rate. So these are this is the correlation matrix, just graphically, what we would expect to see in our parameters that we put into the kinematic models. And we looked at the joint distributions as well. In other words, here's the kinematic slip divided by the average slip compared to the rise time, and there is a correlation. Whereas if you look at kinematic slip versus rupture velocity divided by shear wave velocity, the correlation is there is no correlation. And so we looked at different values to look at these joint distributions, and it makes a difference. In other words, one of the things we found that made a big difference is how rough is going to be the stress on the fault, which leads to basically how rough is the slip on the fault. And one of the things that we found is that if you have a very smooth rupture, relatively, it doesn't look so smooth, but it's highly correlated, what will happen is that you can produce super shear rupture velocities, whereas if it's fairly rough, you tend not to produce these super shear rupture velocities. And so we can look then at even the peak slip rate and say, well, how is the peak slip rate correlated with these values of the autocorrelation function of the slip? And again, we can see that we can get some very large peak slip rates if it's highly correlated, whereas the values are much less and confined to a much smaller, much narrower range, relatively speaking, between 2 to 6 meters per second maybe, that's the outlier, but centered, let's say, 3 meters per second, for values in which you have a more heterogeneous stress distribution on the fault. Knowing the stress distribution on the fault, let's say for the slip, you can choose a value in here at 4, and you can then get the autocorrelation functions for rupture velocity, peak time, and rise time as well. So you can put these autocorrelation functions into the if you'd like, you can you can build these into the kinematic models. And so this is the model that was that's been published in JGR 2010 by Jan Schmiedes and myself and Danielle Lavallee. So the one thing I wanted to say is that this autocorrelation function is we don't know how to choose this all the time, but it can make a very big difference in the ground motion. And depending whether or not you have a very heterogeneous, you get a much more standard rupture. So what these stochastic models that are extremely heterogeneous, you would expect to see sub-shear ruptures and very classical, let's say, ground motion. But you can see that if you went to, as you go to more and more correlation, the ground motion is larger. This one is a super shear, ruptures off the fault, extending out. And even at nu equal to 3, you get a much greater ground motion amplitude. You can see the amplitude of the ground motion is increasing. These are all on the same scale. And you can see that the ground motion is going to be affected by just how strongly correlated our ground motion is. And the one thing, too, is that I want to make a point here. I'm going to stop. Is that, we took the two models. And we took the models of Liu, Archuleta, Hartzell, and then we took Schmiedes, Archuleta, Lavallee, and we compared these models for the same 20 runs. And the reason for doing it is we were calculating them at stations, same set of stations, let's say Northridge. We ran the same set of problems in the same Green's functions. And so we looked at the bias, the standard approach. And the reason I point this out, it relates to what I'll talk about this afternoon. This is the idea, one of our standard metrics, okay? And they look about the same, okay? But, if you look at the predictive power of these two methods, it turns out that what we're plotting here is this percentile is the ratio of the number of stations with PGV observed greater than the synthetics. So this point over here at 0 means that what we have then is that the synthetics are overestimating the observed. So we did 20 different runs at 44 stations, and we then looked at, so the percentile is the number of stations where PGV observed is greater than PGV synthetic divided by 20, the number of models that we ran. And So what happened is that what you see is that LAH, because of this correlation between the rupture velocity and the slip, we're actually producing a larger amplitudes in our synthetics. Whereas the method over here that is Schmidus et al., we have a different one. It's a better uniform distribution. And so when you're looking at the predictive power, perhaps it's possible that, even though the bias, because the bias will basically weight over-predicting and under-predicting, and if you average it, you come out with zero bias. But in fact, it may not be the best indicator of what method we should be using. And so the thing about it is that these dynamic ruptures, the type that SSHAC has actually been pioneering now and doing with these, basically having people compare their methods to make sure we're getting the same output numerically, even if if we're running the same physics problem, we should. Then what happens is we can use these dynamic models to guide the kinematic models. And this is the only way. We just won't have enough data. When you look at earthquakes, I mean, it's hard enough to invert the data, trust me, to say anything about what's happening on a fault. And the only way that I think that we can get these correlations is by getting them out of these dynamics, these dynamic models. And I would point out that these dynamic models, right now all we've looked at are strike slip. We haven't looked to see what would happen if there's a different set of correlations if we look at dipping faults. We've run a couple, but not enough to do the statistics and produce the marginal distributions. But I think these dynamic models provide us some insight in the direction we're going, and they're the type of information that we're going to need in order that we don't produce, I don't know if they're unrealistic, I would say they're unphysical ground motion estimates. So I'll stop here since we're a little bit over anyway. Thanks.
Yeah, there's a bunch of Mac people in the audience here. So I'm familiar with what Ralph has done. We were supporting the work that Jan had developed. So this is one model that has been pushed all the way through to creating a rupture model generator. One limitation that he noted that's important is this was the correlations for the subset of cases that were sub-shear. We need, in evaluating our full range of what goes into the kinematic models, have to get the super shear cases. So can you talk about what else would have to be done to build up the super shear part of that model?
So, yeah, I forgot to mention, on Jan's committee, on his PhD committee, Professor Norm Abramson was one of the committee members, so that we wanted to make sure that basically that we were doing, getting these correlations. But in the super shear, we deliberately chose inside. We tried to keep having the experience of knowing what basically what the autocorrelation function was and what it should be. But we could do the super shear case if we wanted to, if we ran more models with the higher degree of correlation of the initial stress. And we would then find the models and we would then look to see what the correlations look like by taking that same rectangle and trying to determine what the correlations were. We deliberately took out of any time that there was inside that box an area that had super shear, we excluded that in our calculation of these distributions. It's a matter basically of going back and running a large number of models in which we enforce a autocorrelation that basically is 3 or 4 in the exponent on stress, and then we would in fact find super shear ruptures. And it's a matter of doing 300 more ruptures. It's doable.
And related to that, this is all out of my topic area, but is the S parameter that you chose, right? And you didn't talk about that here?
No, I didn't talk about that.
So
the other parameter that is affecting whether or not you get to super shear is what is known as the strength, the seismic strength parameter, or this, which is the ratio when you have three stresses. I have it. So the S parameter that will also affect whether or not you get super shear is the ratio between the distance between the strength, the peak strength, and the initial stress relative to the stress drop, which is the ratio, which is the difference between tau naught and sliding friction. So you could imagine that if your initial stress is close to the peak strength, in other words, so that this distance is very small, then when you have a stress drop, you are really close to pushing the next domino over, because all you did was you just triggered one, you had a big stress drop, you're already pushing on the next domino, but the next domino just is almost tilted because it doesn't have to get this stress doesn't have to get very high before the next point in the fault says I'm going to rupture. And so if you have then the case where the initial stress is close to the peak strength, then what will happen is that you can in fact generate a super shear. This has been shown by, analytically at least for a homogeneous material, shown by Eric Dunham, that if the ratio is less than 1.19, you can generate super shear. So typically what you do is you keep this stress higher than, this ratio higher than 1.19, and then you keep it uncorrelated and you will end up with subshear. So when you're thinking about this, what does this mean if tau naught is close to tau p at most parts of the fault? Okay, one way that you might imagine that is that imagine that when you're loading the stress on these faults, that you're practically in a uniform material and a uniform geometry. Okay, so you're nice and straight. So every point on the fault is in fact being loaded almost equally at the same time, approaching this tau strength. Remember, strength is the strength of the rock. So you're getting up near the strength of the rock almost uniformly over every point on the fault. So clearly at the hypocenter, it has to hit tau p, the strength of the rock, the peak strength. But if every other point on the fault is close by, then as soon as you have a stress drop, it means that then everything had to also be close. So in the case where you have, let's say, you could imagine this in the case of where we sometimes, one of the arguments for super shear on these long straight segments is that basically they're loaded under a very large uniform shear stress at large distance over nearly a straight part of the fault in a homogeneous material, then every point should in fact be loaded almost equally. And so if one point on the fault ruptures, it's very close to failure at any other point. And so you can do this by having this strength factor, this S factor, being low. In other words, this tau p minus tau naught is small relative to tau naught minus tau f, your stress drop. And so this is another way that, and it's a parameter that we have not completely explored.
Thank you. That's probably the best physical explanation of super shear. Regarding this, if we're thinking of using these models to develop realistic combinations of parameters for the kinematic models, how are we going to have just a distribution of the ratio of these parameters, or it needs to be included in a holistic fashion, right? So what you generate as models or source correlations, all those parameters, it could be super shear, it could be not super shear, right? So is there a way to integrate that so that we cover everything in one shot? Or you see where I'm going with this? Oh, yeah. Yeah. You don't want to hear about it.
Yeah, now you're asking a really tough one, because now you're asking that in fact We got correlated parameters out after the fact. Now you're saying, well, what happens if these parameters are correlated as the input models into the dynamics? In other words, suppose that the S value, how correlated is S, let's say with this parameter which we call the autocorrelation power, nu equal to 1, 2, 3, or 4. And so to do a full range, you would want to do both. And the one thing we do have that, as shown by a number of people, but I really like the combined work of Ullman and Scheer in particular, and then the Scheer, Pareto, and Hoxton paper as well. And that is that we do find that the stress drop is in fact something that is, it's got a distribution. It looks log normal, or my friend Danielle would say it's Levy distributed, but doesn't matter. It's got heavy tails on it, but it's centered on about 35 bars. And so we've got that distribution, so that tells us what our stress drop is. It's hard to know what we could say about the strength of rocks, okay, and what that has to be. Heat flow would say it can't be much more than a certain number. So it's possible, but it's not something. It's all by itself a big research project as to how we would actually put in a distribution for S, and our S's are heterogeneous because of the nature of our initial stress. But the thing about it is that whether or not we have whether or not we should set that strength a lot higher and force everything to be sub-shear, I just don't know. But I would say that the overwhelming majority of inversions for earthquakes where we have data, the larger earthquakes, do not indicate super shear. The other thing is that you will not see super shear in cases, let's say, where you have thrust faults where it's primarily rupturing up dip, because that is a mode 3 rupture, and theoretically it's shown that you cannot get super shear rupturing up dip, so you have to be in what's called mode 2, where you're, let's say, a good strike slip earthquake, that you would see super shear. And but these mode 3 type ruptures, which are dominantly mode 3, you don't expect to see super shear. You won't see it. Now, if you have something like Chi-Chi, where you have mode 3 and mode 2 mixed, all bets are off. But that's a really big earthquake. But if you have primarily thrust like Northridge or San Fernando, no, we're not going to see super shear, because the rupture and the slip are in the opposite direction.
So for our approach, we need to find aleatory and epistemic terms. And my understanding of what Jan has done is that fundamentally the correlations were different for the subsets that are super shear versus sub-shear. And given that, we will probably need to at least have an epistemic term that's going to be is it going to be 10% of the ruptures are super shear versus is it 20% or something like that? But we'll need to have the correlation structures set up for those two different cases. And if I try to summarize what you've said, the correlation structure that you built up, we now have for sub-shear strike slip. Okay, so we don't have super shear strike slip yet or reverse cases. Correct, okay. Ruth is still here, right? So we're looking at, come on up here, Ruth. We're looking at our data needs, okay? One model for is available that we just talked about, but can you try to summarize, Ruth, how your procedure for getting your initial conditions, how that compares to what Ralph just summarized? Because the 100 runs project is going to be ongoing. As I said, I'm not sure we'll get that ready to use on the NGA East, yet it should be informative to us in terms of what do we do with the available models. That's something you can answer.
So if I'm understanding correctly, you're wondering how we're going to decide on our heterogeneous initial stresses?
How does what you use
relate to what Ralph?
Relate to what Ralph and Jan had used in their approach?
It's pretty similar. We have a slight variation on the initial stress conditions and friction parameters. I think they might have been a little bit different, but it's very easy to do the same thing. That'd be possible. So what we did do is actually a little different. We were also confined to have the magnitude 6.5 for the 100 runs. So that actually had a lot. We didn't think, at first we didn't think it would be that hard, but that actually almost was limiting the choice of parameters we had. So it would be very possible to do the same thing. We are considering for this next year looking at different ways to parameterize the initial stresses though. So we can do the same things, but we could also go in different directions. That's probably not the answer you were hoping for.
I wouldn't want you to do the same thing other than for checking what they've done, but the real question is, as we've gone through where we had a broader group looking at this problem, the workshop that was held back in May, when Ralph and his student did this, that was sort of their evaluation and their group's approach. How much different? I think what we're going to have to do is check at least some of the correlations that are coming out of the approaches that you're using to see if they're consistent with Ralph's numbers, or are they fundamentally different because of the different input assumptions that went into it?
That's doable.
Okay, so we'll have at least the normal faulting runs to check, but those are going to be, and not until we do the strike split can we really compare directly with your current model. Is that right? Okay. What I would like to, on other discussion, is the kinematic modelers that are out there. If we impose this sort of thing into your model, do you have any comments about, are there problems with trying to do this? Other things that this would not fit with the way that you're doing numerical simulations? Paul or Rob or no? Paul, you always have something to say. You have to come up here, even if you're going to say I can't answer it. Walk on up here, Rob. Sorry. This is just, we have to use we want to be able to keep track of what was said.
Okay, I don't have a simple answer to that, but I would say yes, that is the concept for the kinematic modelers that is being pursued. And in my presentation, I'm going to try to touch on that, give a summary of what's available now, but also looking at the path forward and how we may incorporate some of these ideas. So conceptually, yes.
We'll wait for your presentation. Paul, do you have any comments on that?
Yeah, well, first, those talks were both very impressive, and they're showing a lot of good directions to go. I have some questions and comments. Well, first, I would really like to see more about the agreement with data, because we've transformed from kinematic models, which have gazillions of parameters, to dynamic models, which have millions of parameters. And we've reduced the parameters, but there are a lot of things like, a question for Ruth would be, there are many friction laws that are available. You've been using slip weakening, and you mentioned that you were going to do thermal pressurization and rate and state. And the question is, at some point, which of these friction laws actually describes earthquakes, and how do you know which friction law will produce models that are in agreement with data? And a similar question to Ralph. Ralph's next to the last slide, I was very happy to see, because it was a comparison with the Northridge data, although I have to admit the slide went by more quickly than I could fully comprehend. But, my question is, what is the plan for actually showing that these parameters agree with data? For example, one thing one could do, this would be one could aim at choosing a large number of earthquakes in the NGA catalog and simulating. Because other questions that are related, I'm sorry this is sort of rambling, I have a gazillion questions, but I'm hoping Ralph and Ruth can extract the gist from all of this in a response. Ralph was talking about changing nu, the exponent for the autocorrelation or the power spectrum to get super shear, but that also changes your Fourier amplitude spectrum at high frequency, and so how do you know when you get super shear, you're not throwing out something else that's important? And the last comment I have is Sok-Woo Song's done a lot of work on the correlation of kinematic parameters, and he correlates parameters that are spatially offset from one another. And I wonder if Ralph has some comments on that.
So let me work backwards on Paul's while they're still fresh in your mind. Okay. Get to Bluto. But yes, Soo-Guk Song has published a paper with Paul on saying that there's an offset in the rupture velocity and the slip. And in fact, the model that was used was one that was constructed so that it generated this. In other words, that you basically have a high slip region, a high stress drop region, and a low stress drop region, then a high stress drop region, low stress drop region. And, it is possible, as we show with the rupture, that you can do this. Now, we did this in our paper. We looked at all of this. We found no offset. In other words, we looked at the correlation. There's zero offset between the rupture velocity and the slip, or the slip and rupture velocity. And that happens to come just because of a very particular model that Soo-Guk Song used. And it's the model that basically was first put in by Steve Day in 1982, in fact. And that model is very, very much that way. Now, should it even happen? No. Okay, there's a very nice paper by Eshelby, 1957, in which he shows that basically the rupture velocity acts like a massless particle. It has no inertia, and so it cannot be, in fact, driven by it could not be driven by the stress drop. So I don't see that as, I see it as a particular case in a very particular example that Soo-Guk showed up. In other words, a very periodic high strength, low strength, high strength, low strength region. Now, with regard to the idea of whether or not we're going to lose high frequencies, as we go to super shear, it's a paper that you published, and I can't remember the co-author, but it'll come to me. Oh, Bazzari, right, Andreas. So Andrea Bazzari, but showing that how the super shear, you will deplete some of the high frequencies, you gain it back in different ways. It's possible, the biggest thing here, I think the biggest question is how often are we going to compare, or how do we compare this with data? In other words, when we have the data, it's how do you show that basically that these models are going to be consistent with the data? At the present time, we've run, these dynamic models have been run, fully dynamic models have been compared with data with Parkfield, the paper by Chaumont and myself. There's a paper by Pascal Favreau where we looked at, with me, where we looked at Imperial Valley, trying to see, again, the super shear case. But there really is an issue on these models of saying, well, how well do they capture data when in the ensemble? In other words, because that's what we're really doing. We don't know what's going to happen, and we're going to run many of these. We're going to get average values of average amounts of slip rate, et cetera, et cetera. And it's a big task because we have to run these models against, in particular Green's functions. It's difficult. But I think that when you look at the correlations that we have, in other words, the correlations that we find when we look at the inversions, people will argue how good the inversions are, but even if you take all the inversions and you look at the correlation, which Danielle Lavallee has done, you get an idea of what that correlation function looks like. And generally that correlation function is not, that exponent is not around 3 or 4. It's less than 2. It's typically on the order of 1.2. So it means that what it tells us is that the stress in the Earth is very heterogeneous. And so I would say super shear is the outlier. In other words, it's a particular case, judging from what we've seen so far from the data. But again, getting ground motion out of these, it just takes a lot of time. In other words, we could systematically say, choose 10 or 12 earthquakes and let's just start going through it and seeing if we just run this randomly through here, can we generate some measure of the data? But it's not trivial, that's for sure. But I would say that some of the parameters are better constrained than others based on what we've seen from the analysis, the inversion of ground motion data. But Ruth can talk about how good those friction laws are, because and how important are they to actually have pressure thermalization. I would point out one thing before Ruth takes over. There's another paper that is written by, it's published in JGR. It's by Daub and Carlson, D-A-U-B and Carlson, C-A-R-L-S-O-N, and which they compare the rate and state friction law with the slip weakening law with their free volume law. And basically, you have the same number of parameters in each of those when you put them in, and they get basically almost the same slip rate functions and almost the same rupture velocities, indicating that you're going to get the same output with a given stress distribution.
Okay, Paul asked the important question about fault friction, and I think if I could answer it, then we could all go home. We don't really know how faults work, so we're trying all these different things. Slip weakening we don't think is a real physical mechanism, but as Ralph just mentioned, it can be used kind of as a proxy for some other mechanisms, and it's also possible that you could kind of use it as a macroscopic view, but most likely we should be using rate weakening instead. Thermo pressurization has been explored. I don't think it's ever been done in detail in 3D, and as far as I know, it's never been matched to data in a 3D simulation. So we're still just at the cutting edge of how what fault friction looks like in the lab. I think they're finally getting a handle on it, finally getting normal stresses that are realistic and slip rates that are realistic. And they think they see something and can explain it, but at the same time, these are purely planar surfaces, pure rocks that we don't get anything that simple in nature. So given that, we're exploring all these different things, and then we should check what the effects are of using different friction on the ground motion results. And I think we're still in the exploration stage there. So I know Ralph looked at this some, and I know Paul, you too, have looked at comparing, like in old work with Patty Guacciari, comparing different parameters, even in slip weakening. What can you pull out, what can you not pull out? We have the other problem that when you're trying to infer things from fault slip, we know it's very poorly resolved at depth. So what does fault slip actually look like at depth, and then how do you turn that into a friction law? So we still have so many unknowns, but the question is, how does that turn into our ground motion predictions? And that's, I think, something we still need to work on.
Remember our mantra, what matters, right? We want to work on what matters on this stuff. So I think what may have to happen to do this, the checks versus data, I think what Ruth said is a very long-term and process that I don't think will be quite as easy, but we can look at how much does things change. If we use parametrically a couple of different friction laws, does the correlation change? Now the problem with, that sounds easy to do, but having funded several of these dynamic ruptures, you don't just turn the crank and 100 dynamic ruptures come out tomorrow. These are big calculations and big efforts. So we need to really think about a couple, if we're going to do any sensitivity of this, that we lay out some well thought out cases so that we could see almost pushing the edges as to what is the impacts on the correlations that would then impact the kinematic rupture models, which would impact our ground motion model. So it's a long daisy chain of events. Other comments? Paul? Excuse me? Oh, Paul Somerville. Sorry.
In the discussions about super shear rupture velocity, so far we haven't discussed how likely it is to occur in the central and eastern United States. The way Ralph described the conditions that give rise to super shear rupture velocity, to me, are more likely to be present on major strike-slip faults near plate boundaries with very fairly homogeneous conditions. And I really don't think that it's very likely at all that those conditions are going to exist in the central and eastern United States. So to answer Norm's question, what really matters, my guess is that super shear rupture doesn't matter in the central and eastern United States.
All right. Any other discussion items? Dave, did you have anything you wanted to bring up on this? Or Martin? Bob? No. All right. Yewa. Just kidding.
I think Rob gave a nice talk about those cutting-edge dynamic rupture. But we also need to remind ourselves this is still kind of low frequency range simulations. It's up to like 1 hertz or a little higher. But for the range between, or kind of interest for between like 20 hertz to 1 hertz, how the high frequency will generate what role the dynamic will play is not clear. And for low frequency, actually, the kinematic model already do quite well to match the data. So we just need to some additional constraint from the dynamics, but we really like to see more about what you will tell us about high frequency generations.
But Yewa, we in the calculations that Jan and I did, we went up to 5 hertz, faithfully to 5 hertz in these finite element simulations. And given the size of the earthquake that we're looking at, we're looking at earthquakes basically that are bigger than 6.5 and above, then these earthquakes basically have their corners somewhere less than 5 hertz, more like 1 hertz or less. So we have captured most of the energy basically in these earthquakes. Even if we don't have all the high frequencies, let's say 5 to 10 hertz or 5 to 20 hertz, the thing about these earthquakes is with their corners down around 1 hertz and lower, if you look at the peak, in the velocity spectrum, it'll be peaked in at the corner, which is where most of the energy is being radiated. And so we're capturing, for these bigger earthquakes, we're capturing then the right period range. Now, what we're not capturing, which is involved in NGA East here, is we're not getting to those lower magnitude, let's say 4.5 earthquakes. That's for sure. I mean, 4.5 probably has a corner somewhere around 5 hertz or 3 hertz, so we're right at the edge. But for the larger earthquakes, we've captured the central part of the energy very well.
All right. Thank you. We are at our break, so we will start back up in 10:45 with Rob going over the kinematic rupture model generators. Thanks.
But using them out. All right, well,
Yeah.
I'll sum up here.
Broadcasting is the only way that we most participants can follow.
Yeah.
But it just
Yeah.
Okay, everyone, we're starting. Come on down. Please take place. And Rob is migrating towards the front. Mouth full. Oh, I didn't see the bagel. Oh, thank you. I'll just wait for people to settle down. Simmer down now. Huh? You think you can? Okay, everyone. So we're going to have Rob Graves from USGS, formerly from URS, not too long ago. We shared the same office. He's going to talk about cover different models for kinetic rupture generators.
Okay. Thank you, Christine. So what I'm going to talk about ties in or follows from what Ralph had talked about in the previous presentation. And the scope of this presentation is really to kind of provide a review of kinematic rupture generators, I'll say methodologies that have been proposed in the recent past, and in some sense too describe or discuss which are available for use by, say, the broader community. So to start with, I want to just give a little bit of background, what exactly is meant by the kinematic rupture description. We've had some of this from Ralph's presentation and also Ruth's in terms of parameters and inputs and how they're described. I will go through a review of 6 or 7 methods. Hopefully I've included most of those that are available. I apologize if I've omitted any, and please provide input on that if there are some that are missing from the discussion. And then I want to conclude with some assessment of the methodologies, and we've talked about this a little bit already in terms of how they're validated, their applicability, and also availability. Okay, so let's get into a little bit more of the details. So in a nutshell, the kinematic rupture description is such that given a fault, a defined fault area, and a hypocenter, a complete kinematic rupture description gives the slip vector as a function of time for all points on the fault surface. Pretty basic. And as Ralph had noted, it doesn't necessarily describe the physical conditions on the fault. It's really just a prescription of the dislocation time history. Now, commonly used parameters, slip, the final static slip distribution, is I think used by all of the methods. And in some sense, this is maybe a parameter that we can actually get some information on. We can measure it on the fault after an earthquake, or we can infer that. Other parameters are a little bit more difficult to get a handle on. For example, rupture velocity. And I will contend that rupture velocity is not really a physical parameter. That is, you can't go out to a fault and measure its rupture velocity. It really depends on other physical constraints on the system, the state of stress and the friction and so forth. And so we infer rupture velocity from looking at slip inversions or the dynamic rupture calculations, but it requires some assumptions about how the rupture actually propagates across the fault, and I'll show you some differing opinions about that in the different methodologies. Another parameter is the actual slip function itself. What does the slip function look like? This could be a broom-type pulse. It could be a crack-like or Kostroff-like pulse. Different models have been proposed, and along with each of those models, assumptions in terms of how you describe those slip functions come into play as well. For example, we've heard about or talked about a parameter called rise time, which I think there's a general consensus on what that means. But if you're talking about a particular form of a slip function, the rise time may mean something different for one slip function than it does for another one. And so we have to be careful about that in terms of how those parameters are used. Okay, for the methodologies that I'm going to go through, I've tried to define or list, not define, but just list what are the minimum required parameters that would be used as inputs. So the size of the earthquake in terms of its moment magnitude is one. The location and dimensions of the fault, that is the length, the width, is it buried, does it come to the surface, and so forth. The geometry, the strike and dip of the rupture planes, also the slip vector, maybe the average slip vector of the rake. And these may potentially include segmentation and so forth. And then the other parameter as an input would be the hypocenter, where the rupture starts. Some of the methods also can utilize additional parameters. There may be some scaling relations that would relate some of these parameters to, for example, stress drop. So you could tie in, say, with a point source or the stochastic simulations. How does rise time scale, say, regionally, and so forth. And then maybe also in the local seismic velocity structure. And these additional parameters, I think, generally are meant as a way to try to tie back into the more physical or dynamic representations. Okay, so given that kind of brief background, some recently proposed methods, and again, I hope I've hit the main ones here. This is roughly chronological. Alexander had just mentioned to me I added a methodology that he had first presented back in 1987 in Russian, so I put that up at the beginning. But we have methods developed by Art Frankel, 1991, revised in 2009, Zhang, Anderson, and Yu, Guattari, Mai, and Barossa in 2004. There's a couple variations of Graves and Potarka. I've lumped the Liu, Archuleta, Hartzell 2006 with the extension that Ralph had just talked about, the Schmedes et al. Work. I kind of consider those as similar types of methodology. Sekou Song and Paul Somerville have a recently proposed method. And then the last one I'll talk about has been developed by Brad Agard and some others at USGS. Okay. So let's start with the first one by Kotsev and Kramarowski. I hopefully got that close. In this methodology, I'll describe it in a general sense, 3D complex fault fracture. And the idea is with a fault plane that is defined, the geometric aspects, the displacement across that fault surface can actually occur in an arbitrary orientation that is both within the plane, that I think commonly we think of as a rake direction, but it also can include out of plane or fault opening, which will add complexity into the radiation pattern. The rupture propagates at least over subregions with a constant rupture velocity. This can be adjusted based on assumptions or prescriptions from a user standpoint, based on assumptions related to the state of stress, whether you think it might be subshear, supershear, etc. The slip function itself is a pulse-like function. It can be modified depending on preferences prescribed by the user, and it has a constant rise time to define the amount of time that the slip, from when the slip starts to when the slip ends. And this can be adjusted as well based on preferences by user-defined inputs. Okay, another method which has been proposed about 15 years ago is by Yehua Zhang and John Anderson, and this is the composite source model. The main elements of this model are that the fault is described as a series of sub-events which have different sizes, and there's a fractal distribution on those sizes, following from work that Art Frankel had done in 1991. One difference, a key difference between the original work, from the original work that Art Frankel had done, is that in the Zhang model, the composite source model, these sub-events are actually allowed to overlap. In some sense that, it may imply that the fault is re-rupturing. I think more conceptually what it says is that at any given point on the fault, the slip function is made up of very complicated behavior. And each of the sub-events has a broom-like pulse, but when they overlap, you actually get the superposition of a number of these pulses, and so you actually get a fairly complicated slip function at any point on the fault. These can be modified for directivity if the rupture is going towards a station or away, and so forth. The initiation time is determined from an assumed rupture velocity from the hypocenter to the center of the subfault. And this method has been applied to model several earthquakes. Art Frankel has done a lot of work on kinematic rupture descriptions. Most recently, 2009, he had a paper where he compared synthetics made with kinematic rupture descriptions against the NGA models. The basic elements of his methodology are that the slip distribution, it can be described as fractal. It has a wave number squared fall off, and the panel here on the upper right shows a distribution of slip for one realization. So you can see you have high slip patches, low slip patches, and so forth. The distribution is a random distribution, but it's built up with these constraints. The slip function is a broom pulse, and the corner frequency is set to the inverse of the rise time. The rise time scales with the value of local slip, and it's in such a way that it scales linearly with slip, and there's an assumption that the average slip velocity across the entire fault is this value here, 2.7 meters per second. So rise time is variable across the fault, but it is directly correlated with slip distribution. And these intercorrelations that Ralph had described, you'll see that there's a number of these, a number of these methods rely on those types of assumed intercorrelations. In terms of rupture velocity, or the initiation time, the plot here on the lower right shows contours of the initiation time from hypocenter here in the center. The average rupture velocity in this method is set at 2.8 kilometers per second, but then this is adjusted depending on the value of local slip. So if the slip is higher than average, the rupture velocity is increased. If it's lower than average, the rupture velocity is decreased. What this does is that as the rupture, and then the actual initiation time is determined by taking this 2D field of velocities and actually doing a wave propagation calculation through that. Again, the assumption is that there's a one-to-one correlation between slip and rupture velocity. And you can see that there are perturbations. These are not just simple circular contours as the rupture propagates away. Whoops, wrong way. Okay. The next method in my list here, Guattari et al., 2004, and this methodology is kind of what is commonly referred to as the pseudo-dynamic source model, although I would say that in some respects, all of the methods talked about here rely on inputs from dynamic ruptures. This one strictly built up some scaling relations by analyzing dynamic calculations. The basic approach is it starts with generating a random slip distribution following the procedure outlined by Mai and Baroza. And this is basically specifying what the wave number characteristics of the slip distribution look like, the correlations. It's roughly a wave number squared fall off. From that slip distribution, certain dynamic parameters are estimated using work that, following on work that Joe Andrews had done, in particular the stress drop and the fracture energy. From those dynamic parameters, and that procedure is kind of outlined here. A slip distribution on the bottom left, calculate what the stress drop is and what the fracture energy. From those dynamic parameters, then inferences or relations are used to get kinematic parameters of rupture velocity and rise time. And those correlations, those relations between those parameters are extracted from analyzing a large number of dynamic simulations. A similar type of process as to what Ralph Archuleta has just described in their recent work. So it's designing or building up these kind of rules, relations, based on an analysis of a large set of dynamic calculations, so that there's simple formulas that can be used to get the relevant kinematic parameters. The other plot that I'm showing here is their assumed shape of their slip function, which is built up of two triangles. What I want to illustrate here is that here's some of the ambiguity about rise time. In some sense, you know, the rise time would be the entire length of this function, the entire non-zero length of it. But there's also, many of these slip functions have a sharp peak in the beginning and then a long tail. And so there's really another parameter, potentially, a parameter that controls the shape of that first peak. And we'll come back to that in just a moment. But that's an important distinction to make, and a potential source of confusion when we're talking about these different methods. Graves and Pitarka, 2010. This is a methodology which is similar in its starting respects to the Guattari et al. That is, it starts with a slip distribution that was generated using the Mai and Baroza, but then it deviates in that it does not use the explicit rules derived from the dynamic calculations, but it uses some general rules of thumb. So, for example, the background rupture velocity is set to be 80% of the local shear velocity. However, there's some perturbations on that rupture velocity that are correlated with a local slip, similar to the methodology of Frankel, such that when slip is higher, the rupture tends to go faster. Slip is lower, the rupture tends to slow down. So that's an explicit correlation between slip and rupture velocity. The rise time the average rise time scales with the Somerville et al. Relations, so it's basically tied to seismic moment, although it's adjusted in two ways. First, it scales with the square root of the local slip. Higher the slip, the longer the rise time. And then it's also scaled as a function of depth, so as is the rupture velocity. So in this model, in the shallow portions of the fault, that is within 5 kilometers of the surface, the rupture velocity is decreased and the rise time is lengthened. And this is based on analysis of recent surface rupturing earthquakes. So this is a little bit of a twist compared to some of the other methodologies. There's also some scaling relations for multi-segment faults. Liu, Archuleta, and Hartzell, which also leads into the Schmedes et al., and Ralph has talked a bit about this. The idea here, again, is correlated random source parameters. That is, the slip distributions have a random component, and the kinematic parameters that are developed are based on correlations among the various parameters. So as Ralph had described, the initial slip distribution is based on Mayan-Barossa. It's mapped to a Cauchy distribution in space. In the initial Liu et al. Formulation, there is a correlation between rupture velocity and slip, which had a correlation coefficient of about 0.3. Rupture velocity is generally about 80% VS, but allowed to vary about that median. There's also a correlation between rise time and slip. And as Ralph had mentioned, the rise time has a beta distribution. The Schmedes, Archuleta, and Lavallee formulation builds on this earlier one and actually modifies or replaces some of the correlations. So it's really an extension of the previous model, but it's basically using the same type of framework. So here's some figures that I think Ralph had shown. And for example, in this model, one of the main differences or the modifications from the Liu et al. Model is that slip and this gamma parameter is rupture velocity have basically no correlation, whereas in the previous model they were strongly correlated. Many of the other models have a fairly strong correlation between slip and rupture velocity. So this is an area that it's a little uncertain what the right way to do it. I think the methodology that's been laid out in terms of analyzing the dynamic ruptures is the way to go about doing it. But in my mind, there's still some uncertainty or some unanswered questions there. So still some work that needs to be done. And okay. Song and Somerville. This is a method that has been proposed very recently and was talked a bit about in the previous discussion as well. The idea here, again, is to develop these correlations and coherence between the kinematic parameters as inferred from the dynamic rupture calculations. And to me, this was a little bit confusing, and I don't know, I'll try to explain, hopefully, just so that everybody understands the idea here. If we have two parameters, say two kinematic parameters, y and x, and we want to investigate what the correlation structure between those two parameters are. It could be slip and rupture velocity, for example. One way to do it is to look at the value at one point, x, at a point, a location u, and see what the value of y at that same spatial location is. Okay? That's a zero offset analysis. What Sekou had proposed is to not only look at that, but look at non-zero offsets. So that is, how does this value of the parameter x at point u compare to the value of y at the point u plus h, where h could be ahead of it or behind it and so forth. And then you can, so you build up this whole very large set of correlation parameters, and you can utilize some geostatistics tools to analyze that and also develop predictive models. Ralph had talked about the particular model, one of the models that they had looked at, which is shown here at the bottom. This panel shows the slip distribution. This is a dynamic calculation, but this is the slip distribution. So you have these very kind of idealized distribution of very high stress patches separated by low stress. This calculation was initiated, say, at this point here, and then basically propagated to the right. This is the local rupture velocity, and you can see this, that in this case, the rupture velocity kind of speeds up as it's going over these high stress patches. And so you do get an offset in terms of the correlation between slip and rupture velocity. That is, if you have high slip, it's actually correlated. You'll get high rupture velocity kind of out ahead of that. SSHAC has done some work on additional rupture models to see if what's kind of demonstrated here in this idealized case is true in a more general sense, and I think that it's not clear at this point how strong these effects may be. So this methodology, again, same type of concept, but it's looking at a much broader set of intercorrelations. Okay. Brad Agard. This was work that was done actually for characterizing ruptures on the Hayward fault. And, but the general methodology, I think, could be applied to other faults. Uses the same type of, it starts with an assumption about a background slip distribution, but extends that to shorter length scales using the Mayan-Barossa formulas. Some interesting kind of features of this model is that Brad has set it up so that it does account for non-planar geometry. You can actually have a fault that bends around a fault surface in multiple dimensions. He has a methodology to account for creep. May not be important in the eastern U.S. And also can look at, say, accumulated strain. You know, how much, what's the slip rate? How many years since the past earthquake? How do you incorporate that information? The rupture velocity parameterization is actually very similar to what Art Frankel had proposed, such that it varies with slip. And Brad has some actually very interesting movies. This is a snapshot of one of his movies, if I can get my cursor. The hypocenter is right here in the middle, and you can see what happens as the rupture propagates away. Say it's going along here, it actually snakes around through the slip patches. In some sense, this may be a little bit more of a realistic model, but it gets back to the point that I brought out earlier, is that just defining rupture velocity does not uniquely define how the rupture propagates across the fault. In this case, it actually snakes around. I find this a little bit interesting. This is the Hayward fault. You can see that it starts out going sideways and then basically comes straight up. I don't know, we may be sitting about right here. Maybe it's just behind us. But there's some enhancements in this model that go beyond some of the more simple correlations that were shown in the earlier ones. Okay, so that is a review of the models that I'm aware of or was able to find in the recent past. Hopefully I've covered most of them, most of the main ones. Now some of these models have been proposed and described and it's kind of without a lot of testing or validation. Others have had more rigorous or more comprehensive sets of tests. These four models, which also incorporate, say, earlier versions of the models, these are the four that I were able to kind of find that had significant kind of comparisons or validations against recorded earthquakes. And so this may be an additional component in terms of assessing the methodologies how one might make a judgment as to whether or not it's acceptable or has it passed a certain threshold in terms of acceptance. There's also an issue in terms of availability, or what is meant by availability, at least in my mind. So if I take from that list and look at, in a very public sense, what is meant by availability, I would say that there's two of those models which are available in the sense that anyone in this room could go to the SSHAC Broadband platform and actually check out those computer codes, look at all the documentation, understand what the inputs and outputs are, and actually produce their own set of kinematic ruptures. And the idea in terms of the broadband platform, which goes beyond just kinematic rupture generators, but the idea is it's designed to allow outside users, that is, the people other than the code developers, to access and run the computational modules. And it also has some standardized input-output formats. I put this out here because I think it's important, at least in my mind, that this is one component of how we assess what is meant by availability of the models, as opposed to, back in the in the earlier NGA work, where individual modelers or developers are being asked to provide inputs, and there's always some potential issues with that. And actually, let me say this. I'm not implying that these methods are somehow have passed a higher acceptance criteria than the others. And in fact, the idea on the SSHAC Broadband platform is that it is designed to be open. So theoretically, any of these methods with, the developers provide the codes and the necessary documentation, they could be put on there. So I fully expect to see this list expanded, certainly in the near future and the longer term. Okay, so given all of that background, here's a list, a very brief list, of some critical issues and needs that I came up with, and there may be some more. So let me just go through these, and then this can kind of lead into the discussion. So most of our experience in testing, i.e. validation, of the kinematic rupture generators has been with Western U.S. earthquakes. That point probably hasn't come up at all in this meeting, right? So how significant is this issue? All right, that's something that I think warrants some more discussion. Second point, the generators are designed or calibrated to produce median values in the sense that, in particular with respect to rupture velocity and rise time. And what I mean by that, as an example, in a given realization, the rupture velocity average over the entire fault is 80% of the shear velocity. And most of the realizations are going to be pretty close to that value. But how often would we expect, or might we expect, a rupture with an average of 90% of shear velocity? So it's not just that rupture velocity has some variation in a given realization, but are we looking at different classes or different, say, target median values? And that's a very difficult problem. Obviously, it was talked about in the earlier session this morning. So how can we develop approaches to better quantify the expected variability of these key kinematic parameters? And maybe it goes even to the dynamic parameters. The last point, what is meant by available methods? Does it just mean that they've been published? Documentation? Are they publicly accessible? Is there some standardization? Do they need to be validated, et cetera, et cetera? And I know this is a topic that has been discussed previously, and I think will be visited as we go along here. And I think, yes, that's it. So I will stop at that point.
Thank you. Now Rob is wondering if you're all sleeping. I don't think so. I think you did a really good summary of what is going on out there and how, and some of the issues we need to consider. Some of them we already addressed, but I think that talking about what we consider available methods applies also to other things we discussed earlier this week. For point source, for example, did we cover the range? Well, there may be tons of models, but we want to capture, I guess, what is that available or reasonable models, and that's a question we really have to clarify. This was good. It highlights to me like some of those, like your second point is what do we constrain and on what do we put the variability in terms of input. I think some of that is going to be flushed out using dynamic ruptures, but to a certain extent we have some input and overall, again, going back to what I guess Ralph is going to cover a few more things on the validation, but what do we consider as a fixed input? What is a variable input? And if you have a fixed input that's internally correlated, like you talked about your 60% or 80% slip rate and rupture velocity, I mean, these are constrained by ground motion validation, mostly, or?
In some cases, yes, but I think also constrained by dynamic calculations. It can be a very subjective process, unfortunately. I think the developers, by and large, of these different methodologies have tried to do a very good job of documenting exactly what they've done.
And their assumptions.
Sometimes it's a little bit hidden, but these are models, and there are assumptions that go along with each case.
Yeah. So again, within this project, we want to cover the center, body, and range, ultimately of ground motions. That includes the variability and the epistemic uncertainty. And my concern when I think about the project as a whole is how soon in the process do we start to include the epistemic uncertainty, and where do we put that epistemic uncertainty? And that includes an input of the rupture models and the simulations themselves. And the kinematic is one part of that. So I think we need to think about this moving forward. I think Norm is preparing more specific discussion points, but these were general comments. While he's getting that ready, anybody has comments or questions for Rob from the resource expert list? You have to come up front. So for those who were not there the previous days, you have to come up to the microphone, because the microphone sound goes through the phone, and that's how our everything is recorded, plus we have people attending online. John Stewart?
Thank you. Now, my understanding is that the simulations using these kinematic rupture models are actually broadband. If I'm mistaken about that, then please correct me. If they are broadband, or at least a subset of them is broadband, then it seems like the discussion of what we're doing at the high frequencies is missing. And there's elements of how we describe the source that would affect even those high frequencies, like the minimum element size where the slip is specified and randomness at those small scales. So I guess I'm not seeing the discussion of the range of models that could be considered for the high frequency component of a broadband model.
Yeah. Okay, so I didn't specifically talk about that because I tried to keep the scope a little bit more limited, but that's a very good point. Some of the methods have been, that I've talked about, actually can be applied to the full broadband generation of ground motions. Now, there's maybe a caveat with that. Those may be restricted, say, to western U.S., where the highest frequencies may be 10 to 20 hertz that we're talking about there. So it's not clear, can it go to 50 hertz? I would say, hopefully I get this correct, I think the composite source model, Zhang et al., can be applied in that sense. The Liu et al. / Schmedes et al. Methodology takes that same basic kinematic model and applies it for the high frequencies. I think the others take some essence of the kinematic description and then utilize a more stochastic formulation at the high frequencies. So, and there are some kind of rules or methodologies on how you would take or what those modifications are, but it does change, in some sense, the kinematic description in order to bring in some more stochastic components. So I apologize for not talking about those details.
So that's fine. So I think as well I can answer what you're asking about, John. As Rob just indicated, the kinematic models that we're using all have some way to generate high frequencies. Okay, all of them have some element of a stochastic or an empirical component that controls the high frequency part, yet the event-specific features are actually pretty large scale. Okay, so we're going, instead of just saying we know the magnitude and a slip pattern, and where the hypocenter started, and the rupture velocity, those types of things. So I think I will, along these lines, and I think Ralph will talk about this as well, when we say what parameters are fixed and what parameters are free in a model, and how we're going to deal with variability of kinematic inputs, we've talked about this before, of really talking about two pieces of this aleatory variability. One is, if I have a past earthquake and I'm going to optimize, say it's on a rupture velocity, then in going forward I must randomize that rupture velocity. So the penalty is you have to then have a PDF for that and this joint distribution, which is what we've been talking about. If you don't, if you say it's always 0.8 of the shear wave velocity and we just use that, our intent is that we will capture the aleatory variability associated with the variability of that parameter in real earthquakes through the calibration or the validation, the standard deviation from our misfit. That means we've got enough earthquakes to be compared with so that we're capturing the standard deviation and that they're representative of the kind of earthquakes we're after. Okay, so we're back to almost the empirical model, right? So there's a limitation that we're at here in all of this as we go to the high frequencies. A lot of it boils back down to how well do you fit empirical data, and that's going to be a controlling feature. All right? Does that help to explain that? So we aren't expecting any of the kinematic models to really be modeling details of high frequencies because we're not going to even give them that kind of information to use. Is that a fair summary, Rob? Yeah, okay. Let me ask you a couple questions. So before you go back, and then I want to make sure the others have a question. Yesterday we talked a lot about stress drop in the point source model and said whatever we're using goes not only with a geometrical spreading and Q assumptions, but it goes with the model. And to what extent do our rupture generators have to fit with a particular simulation kinematic model approach? That is, are they really separate? Should the rupture generators work for our suite of models we're considering, or do we actually have to have a different, model-specific procedure for generating the ruptures? Yes.
I'll try it. Okay. I think the answer is it depends. I think that. Okay. Sorry about that. I think the intent, by and large, of the methodologies is to develop kinematic ruptures that are independent of a particular methodology. That is, the philosophy is it's really a description of the kinematic process that occurs during the earthquake on the fault, and that then the method to propagate the ground motions away from that is independent. The extent that that is realized with the different approaches, I think, is variable. And I don't feel comfortable in being able to say for a specific method how tied in it is, but I suspect that there are some method-specific interdependencies on some of these models, and that would need to be investigated. But in my view, and maybe correct me if I'm wrong, but my view would be that the more attractive or advantageous attributes would be that we had kinematic rupture generators that were basically independent of the rest of the modeling process. That is, how the waves are propagated away. Yes, okay. So Christine was asking me just to expand a little bit in terms of the SSHAC broadband platform. And that type of philosophy, that the independence of the different modules, is largely guided the development of this broadband simulation platform. The idea behind that platform is to have a set of code bases where somebody could come in and say, I want to simulate ground motions for a magnitude 6.5 earthquake in this velocity model, and give me a suite of different ways of doing that. And there's different modules in there. Some modules generate ruptures. Some modules propagate low-frequency ground motions. There's other modules that propagate the high-frequency ground motions. There's site amplification modules. And these can be kind of mixed and matched in different combinations to allow a user to come in and explore the different attributes of these methods. Again, the idea is that the modules are basically separating different types or different parts of the problem. The source description, the kinematic source description, is completely independent of how you calculate or how you propagate the long period ground motions. Maybe you want to use a full 3D finite difference module. Maybe you have a 1D model. Maybe you have a different assumption about high frequencies and low frequencies and so forth. But all of that is independent of that initial description of the source. So that's the philosophy that's gone into the development of the platform, the broadband platform.
So let me run through my list of comments, and then I want to make sure, start to check on some of the others. The correlations, it appears that, Rob, for most of these models, when they're correlated, it's a 1 or a 0. I mean, they're either locked down, like it scales with, rupture velocity scales with slip, or they're independent. Is that true was that the correct interpretation?
That is true for some, but not all. And I know, for example, the Liu et al. Model actually did not have a 1 or a 0 correlation between the parameters. I don't know if that same is true for Schmedes et al.
Not 1 or 0, no.
No.
So, right. And I guess the one Paul did is even more complicated, right? So, all right. Let's move on. Then I think this may have been asked, but let's get back to it again. The correlations that are in these models, are they constrained by fitting, again, earthquake data, or are they constrained by fitting dynamic simulations? And so we know Ralph's is constrained mainly from dynamic simulation, but how many of them, again, would you say are actually data constrained? You had a slide, I believe, that was dealing with that, but can we go back to that one?
Yeah, I'm not sure if I had a slide talking about that specifically. Yeah, go ahead. I would say that the ones that look at developing correlations in a very strong statistical sense are relying on dynamic calculations. Oh.
This. Okay, so when you say...
Okay, so let me try, I'll explain what my intent is here and see if that helps. So the methodologies themselves may have been developed by, say, examining tens or hundreds of dynamic calculations to build up the correlation. I would say, in my view, that's good, but that's only part of it, because then the next test is, well, does that model, or how does that model compare against past earthquakes? And that's really what I was talking about in this slide, is that there's a series of models that have been developed, some of which, for example, the Schmedes et al. Relies very heavily on the correlations inferred from rupture dynamics. But then, is that methodology able to produce rupture models that also satisfy the observed ground motions? And so it does. That's why it's on this one. Now, as an example, I have a methodology I developed with Arvind Patarka, where we didn't analyze the dynamic rupture calculations, but certainly we read the papers and were aware of the work that was done, and so we adopted some guidelines based on those dynamic calculations that went into our model. But our real kind of test was, given that, how well do we match recorded ground motions? So I would view this step as kind of a necessary kind of check that all of the models really should be analyzed by. So, and I don't think all of the models that I had reviewed here actually have gone through this kind of a final step. I apologize if I'm misspeaking about anybody's model, but in terms of what I was able to look at, I think some of the models haven't really been tested in a very comprehensive way against recorded earthquakes.
So I think we're going to have to think about how you do test these. Our approach right now is to test simulation methods against past earthquakes in a validation exercise. Typically what's done is for the past earthquakes, and I think Ralph's going to talk about this, but we'll have our particular source parameters, event-specific parameters that are intended to be used. Again, let's say it was rupture velocity is a parameter that you're going to optimize for the event. You will, for your 5 or 6 validation cases, you will optimize the rupture velocity and see how well you can fit the data. That is not a test of the forward use of your model to predict the distribution of that for future earthquakes until we get such a large number of earthquakes that we're sampling it. So I think we need to be careful about the test of the rupture model generators in terms of the statistics of future earthquakes versus the validation of our kinematic model given the optimized input parameters for what is going to be a handful of earthquakes or a smaller set. So, back to I think what Paul would likely keep seeing, how do we check against the data? It's going to be difficult in this example. And one source of quote data is our dynamic ruptures that we were talking about this morning. But then how well are all of those parameters actually working as well? So it's a continual process. I'm not sure how what I would call these methods being tested against observed ground motions. But, Paul, do you have anything to add to that?
Yes. One way these models are often tested is to take an earthquake we know a lot about, like Northridge, where we know the slip distribution and a lot of the properties, and then put those as inputs into the model and see how well you can generate the data. But the problem is that doesn't test your slip distribution generator. And one approach might be to go through the entire NGA catalog, pick out the earthquakes for which we have 10 or more recordings, and then blind predict them from only the properties you would know in advance, like the length, the width, and for a hazard calculation you'd specify the moment, and you might specify the mechanism, and then blind predict them that way with maybe 10 realizations per earthquake. Now, I'm not saying that's necessarily feasible within the context of this project, but the advantage of...
Just got up. He's scared.
Yeah. Well, he's not running out of the room, so... Yeah. Should I feel threatened? Of course, to do something like that, you couldn't tailor your models. You couldn't tailor your rupture models to every event because it's too much work, so you'd have to do something very broad brush. But that's maybe an advantage in this context.
Yeah, just to add a bit to that, so I think what Paul has just outlined is conceptually what the developers of these methodologies would actually like to do. I would say maybe only a couple have actually tested this, and I think the Liu et al. And the Schmedes et al. Approach, I believe, actually did this for Northridge in the sense that taking a general description of the fault and the magnitude and plugging those in as input parameters and generating a large suite of potential ruptures, generating the ground motions, and then comparing those against the observed motions, and then in some sense say, well, does that distribution produce something that looks like the observed data? And I think their conclusion is yes, and in fact you could go in and say, well, what's the best model? And maybe and it turns out that one actually kind of looks like maybe what people suspect happened in that earthquake. Okay. The other part of this, and I think this has been an argument or kind of a criticism of some of these methodologies, is that there's circularity in terms of how the methods have been developed. That is, for example, somebody would take the data recorded from an earthquake, invert for a slip distribution, and then say, all right, that slip distribution is now goes into my kinematic rupture generator. That certainly, I don't think that's strictly true, but certainly elements of that are in the methodologies. For example, the Graves and Petarka methodology does take some kind of a smooth, long wavelength slip distribution derived from the slip inversions as an input when modeling past earthquakes. So we're not quite there, but I think the elements are in place in terms of doing this more rigorous testing to try to alleviate some of the circularity, and that's always seems to be present. That is not, inverting the data we're trying to predict, obviously is not something we want to do.
Gabriel Toro, in one slight modification to Paul's suggestion, actually, I think it addresses the circularity issue. Instead of trying to predict events, try to predict what the NGA GMPs do for a certain magnitude and distance configuration for a certain subset of cases, but trying to see in terms of the median prediction instead of in terms of the aleatory uncertainties and so on, but again, with the same idea in mind.
There. Sure.
Yeah, I'm not sure if this is exactly the same way. But the work that Art Frankel had done, he did not actually compare his predictions against specific earthquakes, but he's actually comparing against the NGA models. And so in some sense, that's, I think, a more comprehensive test. He predicted ruptures and generated ground motions for those and compared them against the NGA predictions to see how they matched not only against the medians, but also in terms of the variability. So there wasn't any tuning to a specific earthquake. It was more classes of earthquakes. That's kind of what you were doing. Yeah, okay.
We do have a class of simulations in the stochastic finite source method. And one question is, do these approaches for generating slip distributions even work with the stochastic method? Do you have something to say on that, Dave, with the FinSim? Would that? I'm sorry, XSim. Well, if we're put on a finite stochastic method, can you be using this kind of input for it, or is it you need just a completely different kind of an approach? And you need to come up here.
My memory of the XM input is it's much simpler. I think it's a rupture velocity, essentially constant. You can have a variable slip distribution, and that's pretty much it. And there's some other things about the dynamic corner frequency and so on, but it doesn't have a lot of this. Could I jump in? Maybe I'm speaking out of turn. This is wonderful science. It's really interesting stuff. I'm still struggling to know how are we going to use this in this project. I'm really mystified how we're going to use this stuff.
Maybe I'll try to answer that, but I hope it's not mystifying. In this project, we are looking at ground motion in models for simulations in 4 different ways that we've talked about. A point source single corner model, point source double corner model, a hybrid empirical model, and then a finite fault simulation model. The finite fault, we have identified right now 6 finite fault simulation methods that we are pushing through a validation process. Those that come through the validation process and we say we want to then apply them will be used to generate a suite of ground motions, mainly for short distances. So our finite fault simulations are not focused on the 1,000 kilometers, but they're focused on the short distance range. Ground motions. For those to work, we're going to have the inputs to put into the kinematic model. When we've tried this before, where we have just given a series of modelers, generate a magnitude 7, here's the rupture dimension, here are the stations, and give me a suite of 34 realizations of future earthquakes, we have gotten a very large range of median results. Not just variability between simulations, but the averages aren't the same. Yet, each of the models had in the past gone through validation exercises, and they say, my model works, I've got the math right, I've shown that it works. How do we then apply it? So what we're trying to do here is to get some way to deal with part of what I think has been the difficulty is how do you get that whole suite of varying of forward parameters when we're getting large numbers of them, and that may be correlated. The simplest models that may only have a slip distribution and, let's say, rupture velocity, so I've only got 2, now my correlation may not be so bad as when I've got all sorts of other parameters to deal with. But does that help?
So in the class of finite fault models, are you going to include, like Walt Silva's finite fault model and XM as well?
Yes.
Okay, yes is fine. That's a good answer. And the other question is, are the
I thought that the finite fault models were also going to be used to try to get some feeling for where the point source stochastic models might break down, or whether they can be used. But it sounds like these are two independent paths that are going down in terms of simulating the ground motions. I'm sorry for bringing these things up, but I am confused.
That's okay. So when Yewa discussed the 6 models that we're running, 2 of them are finite fault stochastic models. What we're going to do in the end with this, so we will generate them. We'll have a set of stochastic, point source simulations. We'll have a set of finite fault simulations, both with, say, the hybrid methods and say, Yewa's, if they all pass the composite model, and then the stochastic finite fault method. What we actually do with them is going to be is a decision to be made. One approach is to use them to say, this is a check on the base point source stochastic model that has been the main engine for ground motion models in the East, and do we have to vary the predictions off of what the point source model is, or do we need to change that equivalent distance that we're using to get the point source models to let's say, to work? The other way we could do it is actually just say, no, we're going to switch to relying on those being close, and then have a ground motion model that is a mixture of the two. That decision has not been made. Okay, but what we're trying to get here is the data that we need so that we can then do those evaluations and build the model up.
Then let's make sure that if we are going to be using those to essentially combine the information together in some sense, that if we have to put radiation patterns in, or average radiation patterns, or coastal structure, or any of that stuff, that we're consistent between the 2 classes of models.
They will not be consistent in, I think, the way that you're talking about. So the finite fault simulations, that if you're using the hybrid methods or the Green's functions method, will typically have at least at longer periods, a deterministic radiation pattern, and at higher frequencies, something stochastic or whatever that blurs out the radiation pattern. But it's not the same as the number is 0.6 that we plug into this point source stochastic model. And really what we're getting at is going to be comparing those very simple models to these more complicated ones. We're not focused on a site, right? We're focused on a distance, so that we're going to be averaging over things like that. So I'm not sure that that's going to be a fatal flaw for us. It will just be understanding the variability that you're going to see, let's say, azimuthally from the finite fault methods will be much bigger than the azimuthal variability from the point source methods. Okay? That's all moving forward 6 months from now or 8 months when we start to have the simulations to work with. All right? Go ahead.
So in that broad sense, it's going to be made consistent, but not input to input.
Correct.
Exactly. So, and also, I'd like to clarify again, and I'm just going to re-say a couple things you said, but we're going to use a point source definitely for longer distances, and we're going to have the finite fault broadband to a certain distance range, probably 50. Is that what we talked about? Around. And then we'll see how we incorporate these together, if we do, or if we use the finite fault to really constrain the point source that we will use to generate a lot of ground motions, because it's more efficient. And if we'll see if we can do that or not. If not, we'll use them independently. We'll have 2 sets of data that are just going to be used afterwards. So if that makes more sense, or...
Yeah, and we did had some discussion yesterday, I think it was, I'm not sure if it was in our public discussions, about in the East, we do have cases where the big earthquakes are showing up at higher frequencies out at longer distances. So we may have to push the finite fault simulations further than just 50 kilometers.
Yeah, so
and Bob is shaking his head.
But Bob brought that up yesterday. I'm going to paraphrase that. So even when you were in Florida, you saw that the high frequencies were still dominated by events on New Madrid, right? Charleston. Okay, Central Tennessee, New Madrid. Yeah, why don't you come over and say it yourself so we're all clear. That comes from your experience with the CEU SSSC, right? And others, but yeah.
There are many places in the central and eastern U.S., such as central Tennessee, where the seismicity is relatively low, and therefore New Madrid, sitting out at 150 kilometers, going off every 500 years, is dominating the hazard over the whole frequency band, not just low frequency. So ground motions from big events at 100 to 200 kilometers is very important in many places.
Okay, so we'll wrap this up for now because it's time to go eat and have some lunch, and we'll be back at 1.